My dear student, colleagues, and all the viewers who are watching this program live from Facebook page Physics Adda, I'd like to welcome you all to International Physics webinar. Today it's our 59th International Physics webinar. So good afternoon to all, so hope you are well and safe from Corona pandemic. So all we know that we are living in a Corona pandemic situation and we cannot continue our normal academic program inside the campus. So we have to start our online program to continue our normal academic program. So our Department of Physics, Pabna University of Science and Technology has already started its online program, including online classes and online international physics webinar. So we have already successfully completed our 58th international physics webinar, and today it's our 59th. And for those who are new, I'd like to inform that in those international physics webinar, physicists from different countries are coming as a main speaker, and they are delivering their knowledge with our student, and they are sharing their experience with our student. And I think by this way, our students are benefited. And today it's a very special day for our department. Today I'd like to welcome you all to a joint session between the Department of Physics, Pabna University of Science and Technology, and the National Center for Basic Science, Kolkata, India. And we have with us here today Dr. Samit Kumar Roy, Senior Professor and Director, SN Bose, National Center for Basic Science, Kolkata. And he is already connected with us. So I'd like to welcome our speaker. So good afternoon, sir, and welcome to our International Physics webinar.
Good afternoon.
And welcome to our university and Bangladesh through online. So thanks for accepting our invitation. And I'd like to say thanks on the behalf of the Department of Physics, Pabna University of Science and Technology for accepting our invitation, sir. So the main aim of our program is to motivate and encourage our students in this Corona pandemic situation. You know that due to the Corona pandemic situation, we cannot continue our normal academic program. So students must go back their home due to the Corona pandemic. So they may be frustrated due to the Corona pandemic. So we tried our best to encourage them in this situation. So we have started this program from June 21, and we have already completed our 58th International Physics webinar. So we think that it will help them in their understanding physics and encourage them in this situation. So for those who are new, I'd like to introduce that we have divided our webinar into 3 parts. And first of all, we'd like to introduce our speaker with all of you, and then our speaker will deliver his speech, and at the end we have a time. In that time, anybody can join with us, and you can ask question by commenting also. So if you have already come to know the title of our today's International Physics webinar, and title is the Excitement with the Semiconductor Quantum Structure, and the speaker is Dr. Samit Kumar Roy, Senior Professor and Director, SN Bose National Center for Basic Science, Salt Lake City, Kolkata, West Bengal, India. And if we see his educational and career background, you can see Professor Roy obtained his MS degree in physics in 1982 and M.Tech in material science in 1984 and PhD in 1991 from IIT Kharagpur. And he worked as a scientist B for a brief stint in 1984 to 1985 at Solid State Physics Laboratory, Delhi. He joined IIT Kharagpur as a lecturer in 1991 and rose to the position of full professor in 2004 and Professor HAG in 2010. He has served as the head of the Department of Physics from 2011 to 2014, founder head of the School of Nanoscience and Technology from 2014 to 2016, and Dean Postgraduate Studies and Research 2015 to 2016 at IIT Kharagpur. Professor Roy's research interest in the broad area of experimental condensed matter physics focuses on the semiconductor nanostructures, epitaxial growth of quantum structure, nanophotonics of physics of nano devices. His research has run gamut from very practical fields such as pseudomorphic strained silicon germanium carbon alloy, heterostructures of high mobility, MOSFETs to low-dimensional quantum structures. His studies on germanium quantum dots and strained germanium to achieve high emission from an indirect band gap semiconductor are useful to realize silicon-based laser in future. His research results on floating gate flash memory, 2D or 3D heterostructures, quantum dot, infrared photodetectors, and nanowire heterojunctions are considered as significant breakthrough for future nano device applications. We can see Professor Roy has supervised 26 PhD students, another 12 continuing at SN Bose Center and IIT Kharagpur, and more than 50 dissertation in undergraduate and postgraduate levels. He has completed 16 sponsored research projects worth over about 18 crore as a PI, COPI. And Professor Roy is a recipient of the INSA Young Scientist Award in 1993 and Homi Bhabha Award in 2001, and MRSI ICSC Superconductivity and Metal Science Award in 2015, and MRSI Medal Lecture Award in 2007, and CDIL Award in IET in 1997. He is also a fellow of the National Academy of Science (NASI) and in the Indian National Academy of Engineering (INAE) and West Bengal Academy of Science and Technology. Professor Roy has published more than 300 research papers in peer-reviewed journal, one US patent, 6 books chapter, and co-authored a book on strained silicon heterostructures, materials and devices published by IEEE UK. And we can see he has served as a visiting faculty and scientist at Tokyo Institute of Technology, Japan, University of Delaware, Newark, USA, and University of Texas, Austin, USA, Max Planck Institute of Solid State Research, Germany, Queen's University of Belfast, UK, National Taiwan University, Taiwan, and CGU University, Taiwan. And he's an editorial board member of Nanotechnology, IOP UK, Scientific Reports, Frontiers in Material Science, Optics, and Photonics, Switzerland, Journal of Nano Energy and Power Research, USA, and Nanotrends, India. He serves in a number of national committees that include Nanoscience Advisory Group of DST, PSC member on Condensed Matter Physics and Material Science, and International Bilateral Project, PRSG member, Daiichi Center for Excellence in Nano Electronics and Project, approved by the Office of the Principal Scientific Advisor of the Government of India. And you can see his research areas: semiconductor and oxide nanostructures, nanoelectronic and nanophotonic device, flexible and transparent electronic and sensing device, photovoltaic materials and devices, silicon alloy, heterostructures, thin film technology, plasma and ion beam processing of materials. Fellowship and awards, we can see his fellowships and awards, and visiting professors from different universities all over the world, and his editorial members of different international journals, and administrative and other positions he took in different institutions, including IIT Kharagpur. You can see his Google Scholar ID, and his citation number is 7,499. So thanks all for all of your patience. Now it's time to go to our speaker. So thanks, sir, again for accepting.
So Pretam, can you hear? Yeah,
yeah,
some
you can hear.
Right. So can I start now?
Yeah, you can start.
Okay, Pretam, thank you very much. Firstly, for inviting me to give this webinar. So I think this is extremely brilliant move. Particularly, this is very much necessary in this pandemic situation for the students. I also am as a director of one institute, that SN Bose National Center for Basic Sciences. I understand what is the pain that the students are facing in this pandemic situation. So we should try our best as much as possible. And I'm really happy that for your this noble effort. So this will definitely help the students keeping mentally fit and physically. I mean, they will be in touch with the university teachers and other speakers. So this is a great move. Okay, before going to my lecture, so I just want to say that I had very nice friends with Bangladesh. Previously, when I was doing my master's in MTech in Material Science at IIT Kharagpur, so one of my that wingmate was from Bangladesh. But unfortunately, that time we didn't have the WhatsApp and Facebook. So we were really very good friends, but afterwards we are not in touch. And during my PhD days, we had one friend called Professor Abdus Shobhan. He's still there. I'm in touch with him. He has superannuated from Rajshahi University. He was
Yeah,
a
yeah.
faculty member of Rajshahi University. So he has superannuated. I am in touch with him. And particularly this SN Bose Center has a very, SN Bose, you know, the Satyendranath Bose. I mean, he's famous for his Bose-Einstein statistics, Bose condensation. But one very good thing I am sure you know, but for the students, this is particularly for the students, that Bose's main contribution that is actually was done when he was a faculty member at the Dhaka University. So the 1924, that famous paper on black body radiations and Planck's law, which is sent to Einstein, it was written from Dhaka University when he was teaching there. In fact, 2 years back, we celebrated 125th birth anniversary of SN Bose, and we made a very nice film, and this is available in YouTube. So I'll ask the students sometimes, if you go to SN Bose Transfer Center of Basic Sciences, or even in the YouTube, you see Bose on 125. The name of the film is Iconic Genius, SN Bose and Iconic Genius. And we, in fact, we sent our faculty members to go to Bangladesh, went to Dhaka University, and did some shooting. So it is a nice relationship between the SN Bose Center and the Bangladesh as such. So with this, I will start my lecture. I tried to make it a little bit popular in nature, at least in the beginning, first half. And I didn't want to go to my research results, but some of the results we have shown so that the students get somehow inspired or motivated, and definitely they can do a lot of self-study or go back to the literature and try to learn something more. So can I make full screen now?
Yeah, sir, you can.
Yeah, I'll make full screen now. So is it visible completely?
Yes, sir, you can see.
Yes. Okay. So you see that, so this is excitement with semiconductor quantum structures. So we know that, I am sure most of you are in the level of BSc or MSc undergraduate students. So you have taken a course on either in quantum mechanics or solid state physics. But please remember that quantum mechanics also has got lots of applications. You can really do experiment in the laboratory, and that's what we will try to prove here or show here, that we can really make these semiconductor quantum structures, and they follow the rules of quantum mechanics or quantum physics, and from there you get many exotic properties which are not available in the nature. Okay, so since I've started with a semiconductor, this not only happens with semiconductor, it happens on many other materials, oxides, metals, topological materials, 2D materials. But I specifically have chosen semiconductor materials. And I am sure that I don't have to introduce these materials, because these materials are here, there, and everywhere. So if you see that right now you are connecting through this your online link, you are in the heart of your online link is nothing but lots of semiconductor devices, transistor circuits. So as you know that it starts from your computer, mobile, etc. It uses the silicon transistors, ICs, CMOS, all your mobile, cell phones, CD players, TV. I don't know. It's very difficult to name because everything is there. If you see semiconductor, without semiconductor, you don't exist. Our present society does not exist without the semiconductor devices. So we say what not. So why is it so interesting? Because I am sure that you have also read in your undergraduate courses, but just to set the motion into rolling, actually, and to say that semiconductor is very, very interesting, particularly making many kind of devices, electronic devices, optical devices, magnetic devices, because it's some of his interesting properties, which you normally don't get in any other material. Firstly, the conductivity can be varied over 10 orders of magnitude. You know what is resistivity or conductivity. So you can get a semiconductor with a very high conductivity, almost like a metal. You can get a semiconductor with a very low conductivity, whose behavior is almost like a kind of an insulator. So 10 orders of magnitude. You cannot do these things in any other material. And this can be done by simply a method called doping. And this property of the semiconductor can be actually that. The interesting thing is that can you modulate the property, or can you vary the property as per your desire? So that is what is actual device is. The answer is yes. You can vary the property by varying the temperature. The resistivity changes with the temperature. So this is used for a thermal sensor called thermistor. You know that diodes or transistors are made up by doping PN junction, NPN junctions. That can be done by doping. You can alloy 2-3 different semiconductors. I'll show some example. By doing that, you can vary the band gap or band structure of the semiconductor. So the main uniqueness of this nature has given us some semiconductors, but you not necessarily you have only these semiconductors. You can make an alloy with a different material and can get a different properties. I'll show that afterwards. You can vary the property by optical illuminations, which is used called for all your solar cells, LEDs, photodetectors are actually based on a property called photoconductivity. So that is one very good thing of the semiconductor, that it can be used not only for the electronic devices, but it can be used for the optical devices also. Then there are new types of semiconductors which are called magnetic semiconductors. If we apply magnetic field, the property changes, and a completely new field called spintronics are coming in this particular field, so which will be a technology for the future. Similarly, you can, if you take a semiconductor, deposit on a flexible substrate, and you just put some amount of mechanical stress or strains, you can get lots of smart devices or piezo devices. So that is the beauty of the semiconductors. You can modulate their properties as per your desire. Okay, just this is a textbook material. I don't want to spend any time on that, but just I wanted to take some example because I will be discussing some of them during the lecture. So as per our main definition, in our textbook, we mostly see that valency 4, that silicon, germanium, carbon, they are actually called column 4 elements in the periodic table. They are known as the mainly kind of a pure elemental semiconductor. Of course, silicon is the most popular, then the germanium. But not only that, you can make a semiconductor by taking an element from column 3 and make a compound with column 5, like a aluminum phosphide, gallium arsenide, indium antimonide, or indium phosphide. So these are actually called compound semiconductors. Or you can take one element from group 2, column 2, and one element for column 6. So you can make zinc sulfide, cadmium chloride, cadmium sulfide. So you have got enormous kind of choice of making different kind of semiconductors. You can make so we have got elemental semiconductors, we have their compounds, we have their binary 3,5 compounds, we have binary 2,6 compounds. Not only that, you can make a ternary material. Like for example, you can take one aluminum arsenide, gallium phosphide. So you can make a ternary or quaternary materials. The advantage is that, as you know, the semiconductor material comes with a band structure, and because of this band structure, you get a what is called band gap or energy gap. And this energy gap decides that what kind of property you have, what will be the resistivity, or what will be the optical absorption, or will be the optical emissions. So by allowing this, you can go on changing this. So that is the basic of semiconductor. Yeah, there are more semiconductors there. That like gallium nitride is a very, very good semiconductor now used for white light. I'll come to that, maybe one applications. Zinc oxide. So there are wide amount of choice. Just go to a little bit of history, since we are talking about devices, particularly that quantum devices or nano devices. This is all again known to you, nothing new. But all of these things happened for most of the students when you didn't born actually. So you see that the breakthrough started initially in 1947 when that Bangladesh, what so-called India and so-called the Pakistan got kind of a freedom. Then Bangladesh is of course afterwards. So 1947, the first transistor was made in Bell Telephone Laboratory, but the first bipolar planar transistor was made in 1949. So about almost more than 70 years back. But the real breakthrough took place when the first integrated circuit was actually made by Texas Instruments. This is called a monolithic integration. So nowadays we call the chip. You call the silicon chip, CMOS chip. And they demonstrated the flip-flop digital circuit. And then came the first operational amplifier. So this was one kind of a breakthrough region. And then in 70s, about 50 years back, the first 4-bit microprocessor, the Intel 4004, came in 71. within a year it came that 8-bit microprocessor, and then there is no stopping. I mean, it's going like anything. And 1981, the first computer or laptop was made by the IBM PC, and and that's what I'm saying. None of you actually born in 80s. You probably are born in 2000 or maybe 95 or so. So after this first IBM PC was discovered or invented or launched in the market, that there is a kind of a, and as you know, the computer is kind of one of the invention which has changed this life of the mankind. So this is the history. I mean, yeah, this was the kind of a first junction transistor made in 1949, a very discrete 3-terminal, as you see, very discrete one. And this is the first integrated circuit chip actually done by Texas Instruments in 1959. In fact, for this, Nobel Prize was given later on in 2000, in the year of 2000. So the integrated circuit chip really made so much of impact that normally Nobel Prize is given only for the science work, but in this case, somebody who discovered this integrated circuit chips in Texas Instruments, he got the Nobel Prize. I'll show the one photograph there afterwards. And this is the kind of a pioneering researchers, as you know, Shockley, Brattain, and Burdine. These people got Nobel Prize for inventing transistor in 1949. Okay, now this is kind of a little bit of introduction history. Now, where we are moving to? Why do you want to make this transistor smaller and smaller? Why do you need quantum? Why do you need some kind of a nano? The reason is because of this, because you need all the devices to be very, very high speed. And I don't have to tell you what is the reason, because you want a fast internet, you want to download your movies, process your video files, you want to play online games. Right now we are doing some kind of online lectures, telecommunications, all this you need a very, very high speed. You also need low power as well, so that you need a low power so that your mobile phone or laptop battery can run for longer time, and you don't consume too much of electrical power and things become portable. So that is also necessary. And the third thing is that the density of the transistor per chip should be always increased. If at all these things actually are work together to do some kind of scaling of transistor, and today we call that ultra large scale integrated circuits, or sometimes a circuits what we call with a nano electronic circuits. All these are actually driven by speed, power, and density. So I am sure that you have seen these slides many a times in probably some popular lecture or seminar. This is actually that Moore's law. In fact, Moore's law was that Gordon Moore was the kind of he established the Intel. So he has given that time a kind of a trend of device integrations or device scaling, which we are more or less following for the last 50 years. He says kind of every 1.5 years, the number of transistor per chip will increase. So this increases because actually you reduce the number of the size of the transistor. So if you reduce the size of the transistor, the chip density increases. So you see, for last 50 years, in 1970 we had a CMOS or MOS transistor whose gate length was about 5 micron or so, 5 micrometer. Micro is 10⁻⁶. Okay, and today we have actually you have 8 to 9 nanometer. So nanometer is basically 10⁻⁹ meter. So you see that how it has progressed over the last 50 years. Now the question is that you see that we have put some dotted line and then some dots. So what will happen after 2020? Can we really come down to 5 nanometer, 3 nanometer? So we are already come to the regime of actually in 2004, the transistor was made with a gate length with about 90 nanometer. So that was known as the nano transistor, because typically we say if we come below 100 nanometer means we have come to the nanometer regime. So, but now it's very, very difficult to scale because the laws of physics actually changes, and there are a lot of problems with the heat generation in the integrated circuits. I'll show in a very, very simple calculation to you. You will understand that why do we need new kind of transistor. So this kind of scaling will be no longer very good in the future. Suppose today or a few years back, probably commercially available, if you buy a computer It's a very good computer. It will have about 5 billion transistor per chip, and the gate length is about 40 nanometer. Okay, nano I said 10 to the minus 9 meter. And this 2020, where we are today, actually we are, as I said, we have got 20 billion transistors in a chip, and our gate length is about 8 to nanometer, 9 nanometer. And each of these transistors for switching, because as you know that computer is nothing but works on the digital circuit, switching on and switching off. So each of them takes a energy of 130 autojoule. Autojoule is a very, very small number of energy. Joule is the energy. And if suppose it works with a clock speed of 10 gigahertz, probably this chip will be available in few years time probably. And if you try to calculate how much power it takes or how much power it dissipates, so this is the energy 130 autojoules. Auto is 10 to the minus 18, and this is the count of the transistor, and it actually goes with the clock speed of 10 gigahertz into a 10. And if we assume only 10% of the transistor switches off or switches on at one particular time, okay, the 0.1 actually. So the amount of power that is delivered to the chip is about 26 kilowatt. So think of a silicon chip is about few centimeters square of chip, and you are putting a 260 kilowatt power of a chip, and so the chip will be becoming so hot that chip will not work anymore. So the biggest problem in the scaling of the transistor in the future is that the power dissipations. How do you take out this power from your mobile phone or laptop? As you know that if you use your mobile phone for quite some time, it becomes hot because of the same reason. So this is a big open challenge. Now we are coming to from this is a conventional technology to some kind of a technology of semiconductor. Before coming to so-called the quantum structure or quantum physics, we are introducing one more kind of a junction we call heterojunction or a semiconductor heterostructures. See, most of the transistors that are available in the market are made basically with a silicon PN junctions. So silicon is a semiconductor. You can make a homojunction. Both are silicon. That means both P-type and N-type are made of silicon. But if you use two semiconductors to make a junction, semiconductors with the different band gaps, and of course, two semiconductors, their lattice constant will be different. Lattice constant, you know, they are basically the crystals. So the lattice constants of the semiconductor will be different. And this concept was theoretically given by Shockley, who actually invented the transistor in 1949, and one more scientist called Herbert Kumar in 1958. They showed if you make a junction with the two semiconductors, this works much better. This is a much better transistor. In fact, this is true because what about the mobile phones that you are right now using? Use a transistor called heterojunction bipolar transistor, which goes to a very, very high speed. So whatever the Kumar and Shockley gave the concept in 1959, now it is really used in the market in the commercial applications. So how does it look when you see heterojunction or heterostructures? See, I have shown schematically. I know you know semiconductor has got one valence band or one conduction band, and this is basically this is the direction of electronic energy level. So basically, you see that is the maximum of the valence band and the minimum of the conduction band. So SC1 is a semiconductor with a high band gap. This is called the band gap difference between this, and SC2, that means semiconductor 2 has got narrow band gap. So if you make a junction between them, they can be aligned in a different way depending upon different kind of physics. I will not go to that. So these are called type 1 alignment. So in this case, narrow band gap semiconductors come in between the high band gap semiconductor, as you see. There can be a type 2 also. This is a little bit different. You see 1 and 2. So there is a crossover actually, two different band gap, but there is a crossover actually. That so this will be very, very important when you go to the quantum wells. So I'll come to that afterwards. But right now you say that they can align in a different way, either type 1, type 2. So it does not cross here. This is called staggered type of these things. And type 3 basically that the valence band of semiconductor 1 crosses the valence conduction band of semiconductor 2. This is a very, very interesting structure, particularly for seeing the quantum tunneling in a quantum tunneling that happens in quantum physics into a semiconductor structures. Maybe I'll come to that sometime later. So let me skip this slide, or okay, just I have kept it just for one thing that you wanted to know. So heterojunction does not mean that I can choose any kind of a compound and make one material or another. That is not possible, because we have to see that there has to be something called matching of the lattice constant. If you want to make a multi-story building, so multi-story building is made on a ground floor building, isn't it? Base, and base you have got some kind of pillars. On the pillars you make the buildings. So it is exactly the same thing. If you want to make a epitaxial growth of one material or another, so you have to use the lattice constant of the two materials match. And the people have actually found out a lot of data. So you can easily see the silicon does not match with, as you see in gallium arsenide. Silicon is here and gallium arsenide is here. So this is God's choice. Had the gallium arsenide and silicon lattice matching had been there, so then our semiconductor things would have been really one more breakthrough would have been come. But unfortunately, silicon and gallium arsenide does not match. So I cannot grow gallium arsenide on silicon. So the problem in silicon, as you know, is a very, very nice semiconductor with a lot of good properties. That's why you use for 95% of the electronic devices. But probably you may know that silicon is an indirect bandgap semiconductor. So that's why you cannot make a light. We cannot get a LEDs, or you cannot make lasers out of silicon. So that's why you cannot make any optical emitting devices out of silicon. But fortunately, you can make them with a direct bandgap semiconductor like gallium arsenide, aluminum arsenide, etc. But unfortunately, this gallium arsenide, aluminum arsenide crystal and technology are extremely costly. So that's a big problem. Probably I will come at the end to show you that that our world would have been different if this lattice matching was not a problem. I'll skip this one. Just wanted to say this concept of so-called heterostructures was initially used for making a HBT. That is the concept of Shockley and Kumar. And this has been also nowadays used for making a very, very high electron mobility transistor called MOSFET. And that one very nice discovery, that quantum Hall effect by von Kleising, was made on the structure. But I will skip this because of time, but lack of time. Now, from heterostructures till now, we are using that we have considered the electrons as a wave. Electrons are not, electrons are particles. So the question we ask, if you ask the students whether the electrons are particles or waves, so you know Heisenberg uncertainty principle, you know de Broglie's these things, you know that sometimes electron behaves as a particle, sometimes electron behaves as a wave. So in our normal conventional transistors, electrons always behave as a particles. But in quantum, when you go to the quantum physics, you know that electron has a wave function, electron behaves as a wave. So the quantum devices are all considered when the electron is wave. So in that case, we try to introduce what is the de Broglie wavelength of the electron. And you know that de Broglie wavelength, lambda is equal to h by mv, can be easily calculated for the electron. And if this is comparable to the size of the transistor, the gate length or feature size, we call that the electron will now behave as wave. So we can go from the classical physics to the quantum physics. So very interesting, again, history. The discovery of electron, all of you know, was made by J.J. Thomson in 1897, and he got Nobel Prize in 1906. So of course, when electron was discovered, electron was known as a particle only. But his son, G.P. Thomson, his son, actually, in fact, G.P. Thomson is one of them. Of course, there is one more person with him. G.P. Thomson got the Nobel Prize in 1937 because he experimentally proved, along with other things, that electron is a wave. So this is the father and the son. I mean, both are involved in two discoveries, but completely two different behavior. Okay, so pictorially I have shown this. This you have done in probably, if you know quantum mechanics, the first problem in the quantum mechanics that we try to solve after writing the Schrodinger equation, the particle in a box. If you put a particle in a box, in a finite well or infinite well, and what is the energy, what is the wave function, that we try to solve. We are not doing this, we are not going to do that, but schematically I have shown this same thing. So this is, so now you please try to understand why I have introduced heterostructures. So this is, we are calling is a quantum well, like this is a basically potential well, okay, In this case, particle we are calling electron is a particle. Put it in a box. Box means in this case is a heterostructure. This is a heterostructure 1 with high band gap, heterostructure semiconductor 2 with a low band gap, which acts as a well. And then you put one more actually boundary with the semiconductor 1, so that you can put two boundaries. So it's like a bucket. So it now becomes well. So heterostructures, if you do and grow one more semiconductor 1 after semiconductor 2, you get some kind of a potential well. So if this width of this well is more than the de Broglie wavelength, we say that this electron will behave classically. Okay. And if the width of this well is lower than the de Broglie wavelength, or in the, I mean, comparable to the de Broglie wavelength, you know that electron now will behave as a wave. So electron has to be described by electronic wave function. So this is actually quantum well. When this width is comparable to the de Broglie wavelength or lower than the de Broglie wavelength, we call it a quantum well. And where we don't, this width is much more, we call it a double heterostructures, because there's one heterostructure here, 1, 2, and 2 to 1. This is called double heterostructures. So that's why I introduced to you the heterostructures. So now, is this practical? So these things that I just said, you have done in your physics book. So do you really make some semiconductor structures or some structures in the laboratory which can really behave as a quantum well? The answer is yes. As you know, their de Broglie wavelength is given by h by mv. So h by root over 2 m star e. I am, instead of m, I am using m star, because as you know, in the semiconductor, m star is called the effective mass. So it's not the free mass. It's called the effective mass. Effective mass of the electron. Suppose, yeah. Just I want to let you know also that sometimes we call the de Broglie wavelength. The another parameter also can be used for defining the quantum well or quantum physics in a material structure. This is called exciton Bohr radius. Bohr radius, you know, Bohr radius of the hydrogen atom, you know. The same thing that you can get in a semiconductor. If you have an electron and if a hole, as you know, there is an electron in the conduction band and a hole in the valence band. If they bound together, they are called exciton. So you can, if they're bound together like a hydrogen atom, you can calculate their Bohr radius. And if the Bohr radius is equal to the size of the electron, then also you get the so-called the quantum effect. Now, for example, if you take a electron with a mass of 0.1 of free electron mass, and at room temperature, the de Broglie wavelength comes to around 5 nanometer. So what you have to do? You have to grow some structure with 5 nanometer. And I have already shown you that people are making transistor now with 8 nanometer, 9 nanometer. So growing a thickness of film of 5 nanometer is not a problem nowadays. You can easily grow 5 nanometer, 10 nanometer, 7 nanometer. So usually you can easily make this quantum structure. And it all depends, the lambda depends upon actually the free electron mass or free hole mass. For gallium arsenide, the mass is 0.07 m0, and for silicon is about 0.19 m0. So you can say that for gallium arsenide, lambda will be higher compared to the de Broglie wavelength of the silicon. So higher the de Broglie wavelength, better for you, because then you can make the structure much more easily. So you can basically, you can experimentally observe quantum size effect or quantum effect in your devices easily if the effective mass of the electron in the semiconductor is smaller. Okay, so now the question that I asked people, that who made the first quantum device? Of course, I told you that heterostructure was made by, the concept was given by Shockley and Kumar. This is the Kumar. And I told you the story of that Texas Instrument, that integrated circuit chip. This is a Kilby, he got the Nobel Prize. And these three people got the Nobel Prize in 2000. And this the Alpha of IFA, Russia. He got it for quantum well laser. He got it heterostructures. He got it for silicon integrated circuit chip. So this is in 2000. But much before that, somebody gave a concept, some Japanese called Liu Isaki. I don't know whether you have heard of his name. He was working on IBM in 1973. His PhD thesis, he said that electron tunnels in a PN junctions or a tunnel diode. Okay, and he first for the first time he showed that in a solid state device that if there is a tunneling of electron in a p-n junction or quantum tunneling in a p-n junction, you know that that what is a Zener diode. Zener diode is a diode which works in the reverse bias and used as a, you can break down is this is called a Zener breakdown, and this is nothing but the quantum tunneling process. So when Isaki actually wrote his thesis and write a paper, the reviewer wrote the original paper was rejected, basically it was rejected on the referee's unimaginative assertion that it was too speculative. So the referee didn't believe that there is no new physics. But he, in fact, afterwards it was proved that it was a tunneling. So that way, many people believe that Isaki was the first to make a kind of a quantum semiconductor devices in 1973. But of course, as you see that people make quantum lasers later on, Alpha and got the Nobel Prize afterwards. So by introducing this, now I am coming to your almost the textbook kind of a figure that you have seen, that the particle in a box. In this case, this is the quantum well. So this we call conduction band quantum well. This is called valence band quantum well. So electron actually stays in the conduction band and hole stays in the valence band. So you can have two quantum well in a material system. Of course, when the thickness is less than the de Broglie wavelength or exciton board radius. So what happens, as you know, the main thing is that now the electron is described by wave function. So the blue one is the wave function of the electron here, and this is the wave function of the hole. I've shown him two hole here. One is heavy hole 1 and heavy hole 2. You don't have to go to the details. Think of some hole wave function. And if you have solved the infinite well quantum well problem, you know the energy of this electron in a quantum well is no longer continuous in nature. It is discrete. So electron can have either this state, the ground state we call C1, or a fast excited state called C2. And this energy is given by n square h square by 8m star L square, where L is the width of this thing. Now what happens in this quantum well structure? See, that bulk band gap was initially defined by the maximum of the valence band and minimum of the conduction band by this one. But now the effective band gap, since I said that this is the so-called the ground state of the electron in a quantum well, conduction band quantum well, and this is the ground state of the hole in the valence band in the quantum well, the band gap will be now defined by transition from here to here. So what happens? The band gap is increased. You started with a material with a band gap Eg bulk, okay, but it has increased by, this is the EC1 and this is the EHH1, so the band gap has increased. So basically, you can say by making a quantum well, you have made a new semiconductor material, but actually it's not a new semiconductor, the same material, only the thickness of this well is less than the de Broglie wavelength. Not only that, you can tune this band gap, you can change as per your desire, as per your will, if you just simply vary the L, the length of the width of the quantum well. If you make the width lower, actually the energy will be more. If you make the L higher, the width, energy will be lower. Energy will be low. So this quantum size effect this is known as the quantum size effect. This is used for actually making a laser for optical communications. As you know, all these communication nowadays go to the fiber optic cables, and you need a optical communication, you need a laser, and you need a laser whose wavelength is about 1.55 micron, so that it does not get absorbed in the optical fiber. And unfortunately, you don't have any semiconductor which has that particular band gap. So you have to create that semiconductor either by alloying or by making a quantum well. So this is a very, very interesting physics. Not only the physics, it gives you some kind of new functionalities from this particular quantum wells. So it's no longer is a problem of the quantum mechanics or quantum physics. Only thing, please note down, right now we are using the solution for the infinite potential well. But actually in the realistic is called a finite potential well. So what will happen for the finite potential well? As you know, the energy values will change. The quantum concept will remain same. The exact calculations will be different. So I took a numerical example, but I don't have to go to that. If you take some system with take two semiconductors with a indium gallium arsenide, which is used for making a lasers for fiber optic communications. And if you use normally if you use another kind of indium arsenide, indium phosphide, I'm sorry, one is indium phosphide or one is indium gallium arsenide. If you make quantum well of with 5 nanometer, and indium phosphide has got a barrier higher, so you see the band gap changes from 0.75 electron volt to 1.153 electron volt. So that is what is the numerically I just wanted to take that example. So right now, see, you know that what we have done till now for defining the quantum well, we have only changed the thickness of the well, or thickness of one of the dimension we made lower than the de Broglie wavelength. So we call, say, basically we call it a quantum well, because as you know that it was from 3 dimension, so the electron was free to move in 3 dimensions. Now since we are confined in 1 directions, the electron energy is continuous in 2 directions, but is only discrete in one of the directions, so which is called thickness. So I am just, for example, I am showing here, suppose if it is below 10 nanometer thick, it will behave as a quantum well. So the system we right now we call the 2-dimensional structure, or quasi 2-dimensional structure. From 3 dimension you come back to 2 dimension. Then suppose I have got a nice kind of lithography or some kind of a knife, I can make a cross section of this and take a one part of this kind of a wire or rod, where this width is, this height is also below 10 nanometer and the width is also below 10 nanometer, we get something called the quantum wire. Or basically this is called 1-dimensional. That means the electron is free to move only in these directions, but electron will have some discrete energy levels in, suppose this is the x directions, it will be free to move the x direction, but in the y and z directions, its energies will be quantized. So that's why it's called 1 dimension. And for quantum dots, if you just take a slice of that, just like a cake, so that x, y, z, all the directions, the size is comparable to de Broglie wavelength, you get something called the quantum dot, which is called 0-dimensional structures. So basically, you have changed the properties of the bulk material, 3-dimensional materials to 2D, 1D, and 0D. This is also called low-dimensional structures or the quantum structures. So not only quantum well, you can do quantum wire, quantum dots, something like this. So it has got a lot of other so-called effect in the physics. Not only that energies are quantized, but what is something called the density of states. Density of state is basically the calculation of the number of states available or occupied in with the energy between E and E plus B in a interval, in a particular energy interval. And for a bulk material, as you see, if you start feeling that energy is continuous, so that means electron can go anywhere from here to here. So the electrons are not really confined. So that the spread of the electrons spatially or energetically, spread of the electron is very, very high, because the electron can go anywhere in a classical 3-dimensional solid. In case of quantum well, as you say, discrete energy is nature. If you have some electrons, all these electrons will be in the ground state here, and only when the ground states are full, then only it will jump to the next state, and then it will be again filling with this one. So as you see, the electrons are now confined within the well, because you have shown within the well. So not only is spatially confined, is energetically confined. If you make it a quantum wire, you get the energy DOS, the density of state, as a function of energy, something like this. You see that it becomes more and more narrower. So electrons are now more and more confined with a particular energy. And if you get to ideal 3-dimensional, 0-dimensional states or quantum dots, it's almost like a atomically solved state. So basically, you get this quantum dot is nothing but an analog of an atom in atomic physics. So the behavior that you get in atomic physics, you can almost get the same behavior in an ideal quantum dot. So this can give you a laser with a 1 monochromatic wavelength. So that is the beauty of this kind of this quantum dots. Okay, this quantum size effect, pictorially I have shown that, okay, this is the quantum well with a different, as you see, the quantum well with a different width. Or in this case, actually, you can think of a quantum dot. Of course, we are showing 1 dimension, but think of this is in 3 dimension. The size of the quantum dot is larger here. So it gives a, if you take an emission from this quantum dot, it will be red. If the size of the quantum dot is made smaller, there will be the energy will be more. you see the energy. So this is the energy of the transistors. The energy was less, that's red. Now the energy will be more specially separated, so the energy will be blue. So this is called blue shift, and this is called red shift. So as you reduce the size of the quantum dot, there will be blue shift. It gives a blue emission. If you make still quantum dot size lower, it will give a kind of a blue kind of, sorry, this is the green, I'm sorry, this is the green and this is the blue. So this is the blue shift, this is the red shift. And as you see, the energy is now much more. So the thumb rule is that the lower the size of the quantum dot or the quantum well, higher is the energy. That is given by that your quantum physics formula, because it varies as 1 by L square. Okay, so this, in fact, people have seen long back, but without any understanding. Even that Michael Faraday made lots of colloids with a different, he used a different kind of colloids and used to give a different kind of colors. These colloids are nothing but quantum dots in solutions, and that is used for making that semiconductor doped glass. If you go to churches, you go to many other places, you always say color glass. So color glass is nothing but the defined kind of nanoparticles, metallic nanoparticles, oxide nanoparticles of different size embedded. And as you just, I am showing by this curve that this is optical density as a function of energy. And as you see that if you make the size smaller and smaller, actually that size smaller or smaller, the energy actually goes on increasing. So this is called the quantum size effect. And this is nothing but actually visibly you can get a defined kind of color. So this was initially done by the Michael Faraday, but without any reason, but now it is clearly known this is a quantum effect. So probably I'll skip this one again. Now I just wanted to show you one or two devices, few devices using this quantum well structure, because I thought this is more interesting. But now I think I come back to this again, because I showed you heterostructures like this, that two material, but if you put one more double heterostructures, and if I still told you the L is less than the de Broglie wavelength, it makes a quantum well. So this is a single quantum well. Okay. Now, if you repeat the structure or make it growth, it will give you something called multiple quantum well. So that is interesting because you get a multiple quantum well. So the quantum well can overlap the wave function. If the wave function overlaps, that will give a coupled quantum well, and this will give a very, very nice kind of physics. And in fact, if you can continue this one, we call something called a new kind of lattice called super lattice. So in fact, I'm not defining this right now. If time permits, I'll come sometime later. You can do one more thing also. So in this case, it's quantum well, but as you know, that the second problem in quantum mechanics that you take is a tunneling through a barrier. Okay, so quantum tunneling. So if you make a heterostructure like this is a low band gap material, this is a low band gap material. In between, there is a very, very thin high band gap material. As you know, the electron wave function actually can penetrate this barrier if the barrier is thin, then you can get a quantum tunneling. So this is called a barrier structure, single barrier structures. You make a double barrier structures, you make a multiple barrier structure. So basically, you can play with the structures and make new kind of functionalities or new kind of devices. So I'll show you one device first. Firstly, either heterojunction, you can call this a quantum well laser or a heterojunction double heterostructure laser. Only whether it will be quantum well or a heterojunction will depend upon the L. If the L is less than the de Broglie wavelength, it will be quantum well laser. So as you see, this is double heterostructure, one high band gap material, second high band gap material, low band gap materials. So electrons are confined in the conduction band, because this side, the y-axis is basically the electron energy, and if you go downwards, the y-axis is downwards, basically the whole energy. So as you know that electrons always like to stay in the lower electron energy, so all the electrons will populate in the conduction band here, and all the holes also would like to stay in the low energy, so all the holes will actually populate here. So if you make a structure like this is not an atomic laser, it's a semiconductor laser, while the holes are confined in this valence band here, valence band well you can say, and electrons are confined here. And as you know, if there's electrons on the hole, there can be transitions or there can be recombinations, and then you can get a light out of this. And if you make a cavity, you can get a laser out of this. So this is the beauty of this, Now, I told you that not only that electrons are specially confined, the electrons are also energetically confined and the same energy in a quantum world. So the density of states are actually comes into picture. So when it comes to that, it's very difficult go to the get the laser emission, because for the laser, as you know, the result what is you need something called the population inversion. So you have to inject some electron from somewhere, and you have to actually populate the electrons with all conduction band with the same energy, so that they can always giving a emission with a monochromatic wavelength. So this is actually we are showing the distribution of the excess carriers are like this. All the carriers are confined here. So if the confinement is higher, the laser will always getting the lasing emission is very easy. So not only that, the God has also in fact helped us. What has happened? If you see, the two different materials has got two different refractive index, and you know that photons always try to confine in a material with a high refractive index. Okay, and that's actually the property of the optical fiber. So what happens here, since this is high band gap here, the refractive index is low. Since this is high band gap here, refractive index is low, but low band gap refractive index is high. So you see the electrons are confined there, photons are confined. So if you make it a laser, actually both, so basically what you are trying to get in the structure, if you are getting both carrier confinement as well as the optical confinement to get a light emissions with a very nice kind of a very low bandwidth or low width. Now, I am sure that you have done a lot of experiments with the lasers, particularly in the laboratory. Okay, so if you have seen the gas lasers, you have seen the helium neon lasers, you know the powers are actually very high. On the other hand, when you go to your shopping mall, they scan your product with a laser, or laser is there everywhere for actually that in your CD or anywhere. These are actually all are quantum wave lasers. Why they are good? Because they are portable. You can only back the laser by battery. If you put a battery, even the laser pointer that you use for presentation in our offline presentation, this battery goes for days together, because it takes a very small amount of current or very small amount of power. So all these things happens because, as I said, all these things happens because there is a carrier confinement in the quantum well, and the photon confinement also in the quantum well with a high refractive index region. So in the beginning, when the first heterostructure laser was made, the laser was taking a power, the threshold current density, that minimum amount of current that you need, was kiloampere per centimeter square. And today, actually, this is a little bit old data. In 2000, the quantum dot takes about a very small amount of power, about ampere per centimeter square. Probably today's data will be milliampere per centimeter square. So that's why you get away all laser pen, laser writer, laser many things are basically all are semiconductors and quantum lasers. The other thing this quantum well also gives, or quantum dots also gives, I am sure that you, and Calcutta roads is now all displays all in the night. You don't use the incandescent light because they consume a lot of power. You always use the LED or for the white light, because LEDs are good, because LEDs take very small amount of power, less amount of power, and LEDs are very stable. The lifetime of LED is very high. So and so all in the future, in fact, all the our actually lights will be offish, and other incandescent light actually be replaced with the white light. And these are made by one semiconductor called gallium nitride. So gallium nitride, indium gallium nitride, indium gallium. As I told you that you can have a compound semiconductor, binary, ternary, and you make their quantum wells. And you know that white light you can get by mixing a blue light, green light, and euro light. And you have seen just a few minutes back that by varying the width of the quantum well, either you can make a yellow emission, green emission, and blue emission. So if you make a 3 quantum well with 3 different kind of a color, this will give you white light. But actually nowadays, actually what is done, that people have seen that getting a blue LED and getting yellow phosphorus becomes cheaper to make a basically white LED. So this is again one beautiful things which comes from the so-called the quantum well. And the Nobel Prize was given to 3 Japanese people like Nakamura, Amano, and Akasaki in 2014. This is one more great invention, particularly in terms of the energy. Okay, so I think how long should I continue, Pretam? Another 10 minutes, is it okay?
Yes, sir, you can.
So 10 minutes or so, yeah, so that I have some time for some questions. So once introducing this kind of quantum structures, I've shown the lasers, LEDs, you can make something called photo detector also. So as you know, as I showed again a band gap of semiconductor, conduction band, valence band, and as you know that when an electron jumps from here to here, you get electron in the conduction band, holes in the valence band. So if you put a light, shine a light on a semiconductor, and then electrons goes there, hole goes here, and if you just collect them in the external circuit, you get a current called photocurrent. So this photocurrent gives you a photodetector. So now the photon that you will be able to detect, that now actually decided by the band gap of the semiconductor. So you want to whether you make a detect a visible photon, red photon, yellow photon, blue photon, that is okay. So all these things are visible, lots of semiconductors are available. But there are some very interesting applications, particularly in the infrared detector applications. So infrared detector, unfortunately, as you know that infrared, the wavelength is high. So this energy band gap has to be very, very low. But unfortunately, don't have any natural semiconductors which have a very, very low energy band gap, which works in the mid infrared like 10 micron, 5 micron, 12 micron. It's not a micrometer actually. So this can be also done by the quantum well. In fact, in a quantum well, if you get a one ground state and one more confined state, and if the light falls, the electron jumps from, suppose this is a doped quantum well, light can jump from here to here, and this electron can be collected. This can give rise to photocurrent. Probably I have shown a little bit in the next slide. So what I am to show here, that you can almost have a kind of detectors with a black body radiations. You can entirely detect all the wavelength, and particularly if you can detect in the room temperature something like 10 micron, 12 microns, is becomes very, very extremely important for particularly for imaging applications. So maybe I'll go to one example like that. Okay, the same curve that I'm repeating here, that the electrons jumps from here to here. So it's a basically bound to bound state in a quantum well. Otherwise, you can design your quantum well in such a way the ground state is here, and another state goes beyond the quantum well. It goes something called the continuum states. So here to here. So the jump can from the bound to continuum, so that you can easily collect the electrons in the external circuit. Here I have shown you actually. The bound to continuum, it goes from here to here, and if you use a bias actually that your quantum wells will be bent like this, and you can collect this electron, and you can detect in the mid infrared rate. Now, why this mid infrared is very interesting? See, all of us actually emit some black body radiations, even at any temperature. So the advantage in this case, if you can detect my black body radiation that I am emitting, so you can do basically medical imaging of my body, not only brain, every part of that. So this is used for actually imaging of the cancer cell, imaging of the so-called the tumor, imaging of the brain. This can be used for very, very huge biomedical applications. But only thing that you have to detect somewhere. Yeah, I'm coming to this range. A particular electromagnetic wavelength, you know that you start from X-rays, ultraviolet, visible, then you have infrared, and if you infrared to go to mid infrared to far infrared, we call the radiation called something called terahertz. Okay, so terahertz basically the frequency is in the range of 1 terahertz. So 1 terahertz is about 300 micrometer. So if I'm trying to detect a 10 micrometer, that means basically I'm trying to detect a 30 terahertz radiations. So the biggest advantage of 30 terahertz radiation, that terahertz radiations, that terahertz radiation actually interact with the organic molecules and the biomolecular proteins and many other things. So that's why since they interact with these things, you can really detect many, you can do medical imaging, you can detect many other things. The example that I have shown here, this is in this case actually, as I showed, that some detection of the so-called the cancer cells, whether the cancer cell is malignant or not, that can be done by biomedical imaging by terahertz. This is actually one famous project in Cambridge University, used to know as START yeah, sorry, this is the Star Tiger project. And not only that, this radiation is very, very important for security application. If somebody passes in the airport, this person is passing in the airport with a newspaper, and probably this kind of a knife is there, knife is embedded there, but since the knife is not made of metallic, so that was not actually detected in the metal detector. But since if you put a terahertz detector, you can take a complete image of the man, and you will see the man is creating basically carrying a knife. So this is extremely important for all kind of security applications in the airport. I mean, taking the terrorist base camp applications, detecting landmines, many applications. Just for example, this is a chocolate egg, normally chocolate egg, and you see the petals of a flower is actually embedded on this one. You get a radiations, you get imaging, you can easily find out this is a lotus petal. Similarly, the matchbox. So all these things can be done because you don't have a bulk semiconductor which is available with the band gap falling in the so-called 10 micron, 50, 20 micron region. And this can be used only by the quantum wells, what we call inter-subband transitions. If you have two energy states confined in the quantum well, if there is a transition between the one band to another band, we call it the subband transition. So these inter-subband transitions can give rise to this kind of a so-called the mid-infrared or terahertz wavelength detection. This is one example of a laser. As I showed you, the PN junction laser is always a kind of a bipolar laser. That means one P type, one N type. And I made a statement in the beginning that silicon does not give in a lasing action because silicon is the indirect bandgap material. Only direct bandgap material like gallium arsenide indium phosphide gives a lasing application. So that bottlenecks can be actually broken if you make a series of quantum wells and you make a laser called actually quantum cascade lasers. So it is something like that. If you're putting a bucket of water in a staircase, think of it as a staircase, isn't it? Think of a staircase and put a bucket of water in the top staircase, and if you just drop that, if you just put that bucket of water in the top staircase, it will slowly fall down in energy because water wants to come to the lowest energy, isn't it? Exactly the same thing you can do with the electron in a quantum wells, in a cascaded quantum well. That's why it's called quantum cascade laser. You inject an electron in a quantum well, which is at a high energy state. So electron comes to the conduction band, and of course there will be transition from the electrons from here to ground state. It will give rise to a photon, so one laser photon, and the same electron will be, if you put the quantum well in such a way, the same electron will be injected to the next quantum well. Okay, it will come down to make a transition again, and it will go to the again next quantum well. So you can put hundreds of quantum wells together or thousands of quantum wells together. You don't have any restrictions. Only thing, you have to design the structure in such a way that energy alignment has to be done properly, and the growth of this quantum well has to be done with a very, very high precision. In the atomic layer precision, you can get some kind of a quantum cascade laser. So this has been first demonstrated in the Bell Lab in 1994, and this quantum cascade laser is nowadays used for making a terahertz laser or mid-infrared laser. So this was done by Fest and Capasso, and everybody believes that this particular one will also get a Nobel Prize in the next few years or so. So I just told you earlier that something from the quantum well, you can get something called the super lattice. So if you make a multiples of quantum wells and put the quantum wells very close to each other, their wave function will start overlapping. Okay, so this is a quantum well 1, 2, 3, 4, 5. If the wave function starts overlapping, actually what happens? So, and if you make this quantum well with a perfect periodicity, you know that our band structure or the bands in energy bands in solid happens with the periodicity of the atoms. So similarly here also, since the electron wave functions are periodic in nature and quantum well are periodic in nature, they will make, each of them will give some kind of band in each quantum well. And if they overlap, so this state actually will make a band of energy levels. So that's called actually subbands. So there is one subband here, the ground state subband in the conduction band, and this is the first excited subband in the conduction band. So this is called a kind of a super lattice. Why we call super lattice? This lattice does not exist in nature. You have synthetically made some kind of periodic structure to get this kind of structure. So you can make a lasers, you can make a detectors out of this superlative structure. So many things can be done. As I said, the tunneling through barrier also can be done in a quantum well. So this is known to you that if you make a barrier like this, if you make a single barrier, the electron function will be like this, and electron will penetrate, and there is a finite probability of penetrating the barrier. So, and a very common example normally we teach in the class is basically something called a scanning tunneling microscope, where you can take a atomic resolution imaging of an atom. This is nothing but a metallic tip. If you put it in an atom and bring it very, very close, so when the tip becomes very, very close, comes to the so-called the electron cloud of these atoms, and you see as these things are not at the surface, is never rough in the never smooth in the atomic scale. So as you see that when this tip is moving from here to here, when it was at the top of the atom, the current was high. When it goes to the valley, actually the current was low. So this is the current mapping. So this current mapping is nothing but actually the mapping of the surface of the atom. So this is a gives rise to atomic resolution imaging called the scanning tunneling microscope. So all our quantum structures and nanostructures devices can be easily examined by this kind of microscope with the atomic resolution. So you can make devices also like this. That I'll skip this one. Probably I'll just go to my last part of these things in next 2 minutes, so that I finish it off. I am so till now actually we have shown you the quantum well, quantum wires, quantum dots, and how we can get a light detection, light emissions. You can make a quantum wells to super lattices. So now, as you know, most of the what I've called the electronic communication is done actually through the, of course, the optical fiber communications. But all the transistor itself, actually, they are actually electronic transistor. But have you thought of what is the problem? I showed you one problem. The one problem is that it shows 260 kilowatt of power. It takes 260 kilowatt of power in a modern IC devices or a next generation IC devices. So it is impossible. Why it happens? Because as you know, the flow of the electron always give you current, and if there is a current, there is a resistance. There is called something IR drop. So there is heat. But suppose you think of, can you do this so-called the switching or the transistor by photons? The photon does not have any charge, so of course that will not give you any current. And second thing is that photons are actually much faster compared to electrons, so it will have an extremely fast integrated circuits. So you can basically say from electronic integrated circuits to photonic integrated circuits. So I'll show why it is very important here. So the slides that you see, that if you do an internet search of Satyendranath Bose, you immediately within 0.6 seconds or so, you get how many? That's 1 crore 18 lakh results or something like that, 1 million 18, something very, very high results, and you get a lot of information about SN Bose. But of course, this information does not come to you free. It costs some energy. Forget about the cost of the data. It costs you some energy. What is the cost? This is a typical example. Don't take it as a kind of a number. This is just giving an example. Energy used by a single Google search is equivalent to turning on a 60-watt light bulb for 17 seconds. Okay, now the students, you can calculate that how long do you do internet search per day, and you can calculate how much of power that you are consuming. Of course, you can say that, okay, my electricity is cheaper, or my father is rich, so I have no problem, I can do. But globally, what you are doing, you are using the fossil fuel to generate the electricity. So this is giving us a global energy crisis. And this crisis is very, very huge. Just I can tell you, I can show you some data. So this I have taken from some data. See, the Google data center has a power demand of about 80,000 houses. I think this is a very old data. Probably nowadays Google data center will be much larger, because you know that now the data science, big data, all these things are coming. And next, read the next line, which is very, very important. Providing 33% of the world's population with a 10 megabit per second internet access, which almost all of you are having. That's why you are actually having these online seminars. Would currently require 50% of the world's electricity capacity. This is again old data, about 1 terawatt. So try to imagine just simply using the data, if 1/3 of our global people use the data, we consume at least 50% of the electricity. So not your air conditioning machine, not in your washing machine, not your electric train. So it's huge amount of data energy is used for these things. Because the reason is that I told you, because you have got so many transistors and they take lots of power. So the solution that I have told you already, but I have pointed out you here. If I do a optical switching instead of electronic switching using the photons, basically the photons does not carry a charge. Photon bandwidth is very high and photon is very, very fast. This can break through all those problems. So it can be really pure silicon photonic integrated circuits are yet to come in the market. If it comes to the market, it will be again a huge breakthrough, particularly for big data and many other applications, particularly internet applications. So it will be almost like a chip on your like any MOS transistors on any bipolar transistor. You have something called electron source or the source, then the electron that you can control through your gate, and the electron is detected at the drain. The same thing you can do here. You can put a light source, guide the light in the waveguide. You can modulate the actually the photons, and if you do the detections, is nothing like a simple MOS transistor. But one of the biggest problem to get a silicon photonic integrated circuit chips, which are actually compatible with silicon CMOS, I told you, because silicon does not emit any light, because it's an indirect bandgap semiconductor. So that's why you don't get a light out of silicon. So that's why I told you, if the God would have given us gallium arsenide and silicon lattice constant the same, probably we have seen this chip today. All of us would have been used much faster internet and much less energy consuming devices, because gallium arsenide gives the light emission, silicon does not. So we have to use some kind of hybrid technology. You have to put gallium arsenide or indium phosphide laser on a silicon chip. So this becomes very costly. So this so-called the quantum structures or the nanostructures probably can solve this problem in the future. So just this is only research slide, probably I put it here. This is one, in fact, this was done by the Bell Lab or somebody called Kanham. He made, this is a silicon wafer in his hand, and you can see this is the orange color of the silicon. When the light falls here, basically you get a orange luminescence, because this silicon here electrically etched, which is called quantum wires of silicon, so nanowires of silicon. So that means it shows that when the silicon becomes quantum confined, or if you make a silicon quantum structures of silicon, it does not follow the bulk band structure of silicon, which is the indirect band gap in nature. So it basically bypasses the selection rules, and there is a possibility of getting a light emission from indirect band gap semiconductor, which becomes quasi-detect. So in our lab, or many other people are doing that, trying to make a silicon nanocrystals and try to get a laser out of that, get a light emission out of that. And as you saw that by varying the size, you can change the wavelength. Sometimes people are trying to putting in this case, an example is that using a tin germanium semiconductor, which is normally indirect band gap in nature, but if you quantum confine and put some amount of strain, it becomes a direct band gap in nature. So all these things can give you probably next decade or so some more actually advances in a photonic integrated circuits. So right now we are calling silicon electronics. For the next generation, we will call the silicon photonics. And people are already predicting the market of the silicon photonics will be one day more than the market of the silicon electronics. So yeah, this is one chip that already has been demonstrated by Intel about a few years back. The single chip processor that communicates using light. So yeah, this is almost like a chip, your microprocessor chip, but of course the sizes are bigger, and it does not have a billions of transistors, because in this case you have got, see, these are kind of these are small region are called actually silicon CMOS memory, and these large regions are silicon, also called the optical integrated circuits. So maybe the density of the optical components about 50 to 60,000 per chip, but this can be of course billion transistor per chip. So this is a hybrid between the electronics and photonics. So already single chip processor that communicates using light. So what I was telling you, future microprocessor with a photonic communication that is definitely a good feasibility. So with this, I think let me thank you. And this is my research group at IIT Kharagpur. Of course, some of them have already left. Rishi has already left to USA, and last month he published a Nature Photonics paper on showing the light on a silicon using 2D materials. Shubhrojit is already in Israel. He's also doing a very good there on 2D work. Roop is leaving for France. Orijit has already gone to Korea, but of course, many of them joined back. So these are the acknowledgements. So all this work, the research work, which I have not shown, of course, is all done by the students, and I'm really thankful to them for a good work. And this is right in front of my IIT Kharagpur Department of Physics. So of course, you are all welcome when you come to India for some visit the IIT Kharagpur, come to our department, and we'll be very happy to show you the lab. With this, I end up.
Thank you,
So,
sir,
Pretam,
for your nice presentation, sir. So I think students have learned a lot of things. So we have got some question in inbox. So if you allow,
Sure.
you can read it out.
Sure. Please.
So last question is, what is the semiconductor heterojunction?
Okay. So see, as I said, when you call it, suppose you take a silicon and make a PN junction, we call it a homojunction, because we are using one kind of material only, silicon. Okay. But if you take, as I said, if you take two different semiconductor materials, like for example, I take one material is silicon, other material is germanium, and if I grow one material or another, I also make a junction, or make a one material like gallium arsenide and another material is indium phosphide. So that's why it's called hetero. Actually, two different material is hetero. So two different material with two different energy gap. If we grow one after another, we make a heterojunction. That is heterojunction.
Sir, thank you, sir. We have another question. What is the ultra precise quantum dots?
Yes, ultra precise quantum dots. Actually, what has happened? The biggest problem in quantum dots fabrication is very difficult to, because you have to make a billions or millions of quantum dots in a chip, isn't it? Just like a silicon transistor, ultimately, if you want to make a laser array, you have to make a millions of them. So ultra precision means, if you see the thickness of this quantum dot, the size of the quantum dot, we are talking about 5 nanometer, isn't it? Now the question is it 5 nanometer? What is or one is 5 nanometer, one is 7 nanometer, one is 8 nanometer, one is 4 nanometer. And we have shown if actually the sizes are different, the properties are different. It emits different wavelength. So unless you make all the quantum dots with a 5 nanometer size, you cannot get a laser like atomic laser. See, in the atoms, as you know, the atoms, when you say lasers made of atoms, all the atoms of the same size, because that's the atomic size or atomic radius that is given by the nature. On the other hand, quantum dot we are trying to synthesize. So if you synthesize in the lab, it's very, very difficult to make all the quantum dots of the same size. But there are some technology called the nanolithography. By nanolithography, you can make quantum dots of the same size. So that is actually basically with the ultra precision measurements or ultra precision dimension, you make the quantum dots of the same size, so that you can almost say that I have made a atomic kind of states in my silicon chip.
Thank you, sir, for your nice presentation and discussion. So we have got another question, but for that I need to speak Bangla. So,
Sure.
And this is a different question. So if you allow, I can read. So
Sure.
মেঘ আকাশে কিভাবে ভাসে থাকে আর রংধনু সবসময় পূর্ব আকাশে দেখা যায় কেন?
ওকে, কারণ আচ্ছা, মেঘ আকাশে ভেসে দেখা যায়, অবভিয়াসলি এটা তো অবভিয়াসলি দ্য ডেনসিটির উপর ডিপেন্ড করে, যে আমাদের যে মেঘ মানে আমরা তো দেখছি বেসিক্যালি যে আমাদের অ্যাটমসফিয়ারের অনেক উপরের জিনিসটা আমি দেখছি, তো অবভিয়াসলি ওদের যেহেতু ডেনসিটিটা কম, সেই জন্য ওপরে আছে, এবং সেটার যে তার লাইট থেকে বা তার এটা থেকে আমি সেটাকেই ক্লাউড হিসেবে বলছি। ক্লাউড বেসিক্যালি ইজ নাথিং বাট এ different levels of different layers of atmosphere, nothing but a cloud. And obviously যেহেতু সবসময় আমাদের এই যে ফেনোমেনাটা আমরা যেটা বললাম, যে আমি লাইট যেটা বিভিন্ন কালারটা দেখি, এটা কিন্তু স্ক্যাটারিং অফ লাইট। আমাদের কেন স্কাইটা ব্লু হয়, তার কারণটা স্ক্যাটারিং অফ লাইট, সূর্যের আলোগুলো আসে, কিন্তু আমরা সবসময় একটা ব্লু স্কাই যখন দেখতে পাই, যখন there is no pollution, so the particles are actually blue light is scattered more. অ্যান্ড অফকোর্স সবসময় ওটা যেহেতু সূর্যটা অফকোর্স পূর্ব দিক থেকে আসে, সুতরাং নর্মালি আমরা ওইখানেই প্রথমে দেখতে পাই, কারণ মোস্ট অফ দ্য স্ক্যাটারিং হ্যাপেন্স ফ্রম দ্যাট ডিরেকশন। তো এই ফেনোমেনা গুলো কিন্তু অনেকটা কিন্তু এই যে স্ট্রাকচার যে আমরা বললাম আর কি যে কোয়ান্টাম ডট এমিশন, তার সঙ্গে কিন্তু অনেকটা সিমিলারিটি আছে, বাট দ্যাট ইজ এ ন্যাচারাল স্কাই, ন্যাচারাল ব্লু, ন্যাচারাল সোলার রেডিয়েশনস, and we are trying to mimic them in the lab.
So thank you, sir. We'd like to say thanks again on the behalf of the Department of Physics, Pabna University of Science and Technology, sir. And if we have time after the Corona pandemic is over, so we'll definitely invite you to our university. So I got another question. So if you allow, for last time, I can read it out.
Please.
Can we relate Fermi level with quantum well in any extension?
Sure. Yeah, please repeat again.
So can we relate Fermi level with quantum well?
Yes. So basically, yeah, right. Quantum well also will have a Fermi level, কারণ ultimately সবই তো ডোপিং এর সেমিকন্ডাক্টর মানেই আমাকে ফার্মি লেভেলটা ডিফাইন করতে হবে। কোয়ান্টাম ওয়েলেরও ফার্মি লেভেলটা ডিফিনিশনটা হবে, তো অনলি ডেফিনেশনটা একটু ডিফারেন্ট হবে। আমরা যে বাল্ক ফার্মি লেভেল আমরা যেভাবে ডিফাইন করেছি যে নর্মালি আমরা মানে আমরা মেটালের ক্ষেত্রে যেটা বলি, দ্য হাইয়েস্ট এনার্জি অকুপাইড স্টেট ইজ দ্য ফার্মি লেভেল অফ দ্য মেটাল। ফর দ্য সেমিকন্ডাক্টর আমরা বলি যে ফার্মি লেভেলটা যে লেভেল যেখানে প্রবাবিলিটি অফ দ্য ইলেকট্রন প্রবাবিলিটি অফ স্টেইং ইজ অ্যাবাউট হাফ, দ্যাট ইজ দ্য ডেফিনেশন অফ দ্য বাল্ক ফার্মি লেভেল। In the case of quantum dot বা low dimension structure, definition take too different, but the concept is the same. If I start doping in a quantum well, the Fermi level go up, Fermi level go down. So Fermi level will ultimately defined on the basis of the doping in the Fermi, doping in the quantum dot বা quantum well. যদি ডোপিং না থাকে, it will be kind of intrinsic quantum well, কিন্তু সেটা করা খুব ডিফিকাল্ট, সুতরাং সবসময় একটা unintentional doping থাকবে। So that's why you will get a Fermi level which is আমি যেটা দেখালাম না যে যদি দুটো ইন্টার সাব ব্যান্ড থাকে, একটা গ্রাউন্ড স্টেট একটা এক্সাইটেড স্টেট, so Fermi level we should dope in such a way that Fermi level will be in between, somewhere in between, so that the in normal equilibrium state all the electrons will be in the ground state. এবার যে লাইটটা ফেললাম, লাইটটা পড়লো, ইলেকট্রনটা ওই গ্রাউন্ড স্টেট থেকে ফার্স্ট এক্সাইটেড স্টেট অফ দ্য ইয়েতে কোয়ান্টাম ওয়েলে যাবে। সুতরাং এটা অনেকটা সিমিলারিটি দ্য নর্মাল বাল্ক ফার্মি লেভেল, অনলি ক্যালকুলেশন পার্টটা একটু আলাদা, যেহেতু ডেন্সিটি অফ স্টেটটা পুরো চেঞ্জ করে যাচ্ছে, সেটা ক্যালকুলেশনটা আলাদা।
থ্যাংক ইউ স্যার, আপনাকে অনেক অনেক ধন্যবাদ স্যার। আপনি আমাদের অনুরোধে আমাদের সাথে এসেছেন, আমাদের ছাত্রছাত্রীদেরকে মোটিভেট করার যে আমরা একটা প্রয়াস নিয়েছি সেখানে, তার জন্য আমরা সবাই স্যার কৃতজ্ঞ আপনার কাছে, এবং ভবিষ্যতে অবশ্যই আপনাকে সামনাসামনি আমাদের মাঝে পাওয়ার জন্য আপনাকে অবশ্যই আমন্ত্রণ জানাচ্ছি, এবং করোনা পরবর্তী সময় অবশ্যই আপনাকে আমন্ত্রণ জানাবো। ধন্যবাদ। থ্যাংকস এগেইন ফর অ্যাকসেপ্টিং আওয়ার ইনভাইটেশন। Thanks all for all of your patience for listening our international webinar. So thanks again, sir, and hopefully in the future we'll arrange another webinar with you, sir. Bye for today.
Yeah,
nice.
So glad to meet you online. It was my pleasure. And of course, ভবিষ্যতে ডেফিনেটলি অনেক দেশ ঘোরা হয়েছে, এখন বাংলাদেশ ঘোরা হয়নি, এটা খুবই খারাপ লাগে মাঝে মাঝে নিজে।